We might not have left enough time for everyone to grab coffee. I suspect people will trickle in a little bit here, but let's get started. Next speaker is Greg Michaelson. He's the co-founder at Zerv, a young startup that's rethinking the data science development experience. I like this critical extra fact that on the side, Greg manufactures a line of flavored breakfast cereal toppings called Syrup. And he's going to tell us about how data science accelerated COVID-19 vaccine trials.
So it's 2020, and 3,000 people a day are dying of COVID, and everybody is locked up in their houses, sheltering in place. And the CDC has just announced that predicting the spread of COVID is too hard, and they're not going to try to do it anymore. Meanwhile, I'm working at a startup called Data Robot. And Data Robot was the inventor of automated machine learning. Anybody hear of Data Robot? Okay, nice. Awesome. And so we decide that you not only can forecast the spread of COVID, but that you must. And so we took 100 engineers and we put them on this project, and we said we need to forecast going out 6 weeks on a daily basis at the county level the prevalence of or the spread of COVID, both deaths and infected counts. The data was surprisingly good. Everybody was collecting information, although there were lots and lots of quirks. One notable example is New Jersey. The way they would categorize deaths is that they would decide all of a sudden that a big tranche of deaths were COVID related, and so they would change the coding in whatever system it was that they were using. And then all of a sudden those deaths would appear on the day that they were declared COVID related instead of on the day that the person actually died. So if you look at the New Jersey data, there are massive spikes of deaths, and it's really related to how they cleaned the data and not actually reflective of the reality of what was going on. So lots of really interesting things related to how to process the data, how to clean it, standardize it, since every state and every county was collecting it and storing it in different ways, the lag in which data was updated, and so on. Lots of complexities there. But the utilization, the use of the forecast is actually really important. If you know anything about vaccine trials, you know that in order to have a successful one, you need lots of people being exposed to the particular disease that you're developing a vaccine for. For example, you could never have a Ebola vaccine trial in New York City because nobody's being exposed to Ebola in New York City. And the whole point of the vaccine trial is that you have a control group and you have a test group, and they're both the test group is given the vaccine, the control group isn't. They're both exposed to the disease with the same level of frequency. You can't just expose people. You have to let them. That would be unethical. And so, although people did talk about doing that actually during COVID, never did, as far as I know. But anyway, the idea is that if you can find the areas that are going to be hot, having more exposures, say 3, 4, 5, 6 weeks out, then you can target people to enroll in your trials during that time period. And presumably you can shorten the length of the vaccine trials by just enrolling the right people. And that's in fact what happened. We think we ended up shortening the vaccine trials by about 6 to 8 weeks just by targeting the recruitment of participants in the trials in the areas where the disease was the most likely to be contracted. So when 3,000 people a day are dying and you can shorten it by 50 days, that is a pretty significant undertaking. Now, I don't actually want to talk about COVID because it turns out that was a remarkably polarizing and political topic. In fact, we had one governor tell us when we were trying to get them to use our models that they weren't interested in what the models were saying. They needed the models to say this one particular thing. And if we could make the models say that, then they'd be happy to buy it, which we were like, okay. But so many things like that, like it was, and you all lived it, just like I did. There were certain things that were okay to say and certain things that were not okay to say. And that's how it was, from data to predictions, from the beginning to the end of that particular project. The interesting thing for me was technological, because actually working on this project, it made it really clear that the stack for doing data science and for building AI is lacking when you're trying to do something really serious. There's a lot of irony in the fact that Data Robot, the inventor of automated machine learning, was working on this COVID project because we couldn't actually use our software for it at all, because Data Robot was developed in the 2010s. I think we were founded in 2012. And that was sort of the height of the low-code, no-code movement, if any of you remember. Lots of low-code, no-code tools. Anybody can be a data scientist. Anybody can develop these kinds of models. But in fact, the emperor's got no clothes on that one. Like, everybody's pretty much agreed that low-code, no-code stuff doesn't work. And this project proved that, because we couldn't actually use our software for it. We literally coded it from scratch because the project was unusual. And it turns out that really every project that you work on in the real world is going to have some twists and turns in it, so that these kind of like happy path, low-click or low-code, mouse-driven development environments generally just don't work for those kinds, for really any kinds of problems. And that's what we found. So the pandemic breaks out, and everybody is panicking, and people are dying, and it seems like a real emergency. And so we pulled together this team, this diverse team of engineers, everyone from data engineers and database type people to analysts to actually run the analysis and produce the output, to data scientists who actually did the modeling. And we actually did some SEIR modeling like the guy in the previous talk described. Ours was a really interesting, complex hybrid model that varied by age and by region and by social responsibility and all these kinds of things. It was really a fascinating kind of modeling exercise. But so we had data scientists, and then we also had to have like machine learning engineers to productionize this stuff, because the data was coming in every day, and it would often change in terms of how it was reported, in terms of the structure of the data that was coming in from all the different locations, and how we warehoused it, and then we had to productionize our model so that it could run, and we could run all our simulations on a regular basis. And so the complexity of the system that we were trying to build was not something that could be handled by just one tool or any particular tool. So we had all kinds of challenges, some related to technology. These are things like, we have R coders, and we have SQL coders, and we have Python coders, and they're all trying to work together, but they can't actually work in the same environment because there aren't any tools that support that. And then things like, our data scientists like to work in Jupyter notebooks because, Jupyter notebooks are great for getting... Who's used Jupyter here in the room? Yeah, okay, everybody knows what I'm talking about then. Jupyter notebooks are great for like getting fast feedback because you can write some code, run it, see the results, that sort of thing. Very good for prototyping. But of course, 95% of all Jupyter notebooks are running locally, because setting up a Jupyter server is incredibly hard. But then if you've got multiple people working on the same Jupyter notebook, then you have a nightmare, because GitHub doesn't play nicely with Jupyter. And so code control is a mess, because every time you open your notebook, the metadata changes and creates all kinds of merge conflicts and all that kind of stuff. So the tool that data scientists like to use, Jupyter, is really impractical kind of for developing these kinds of projects if you're working in a collaborative type environment. So you might say, okay, maybe there's a collaborative notebook environment like Google Colab or something like that. But if anybody's ever tried to use Google Colab, I hear the chuckles. It's kind of a nightmare. Colab is like the most ironic name for that tool because, well, anyway. So we were in Jupyter. We're running these complex type simulations on a ongoing basis, and of course Jupyter is an in-memory type tool. So if your browser crashes, you have to rerun everything, and so on. We actually worked with a company at Zerv, the company that I founded and that I'm at now, that actually use Slack emoticons, like the little reactions, to describe the state of their notebooks. Like you'd have to go to Slack and check which emoji was showing under status to find out like which version of the right notebook was the... This is crazy. It's insane that sort of technology exists. So technology, lots of technology challenges, process challenges, things like code control and all that sort of thing, and then collaboration challenges. So I had 4 folks that were working on a particular simulation. One of them was in Austria, one of them was in Singapore. There was me. We had another guy in India, and we were all trying to work. We were following the sun, right? Because we felt like every day, 2,000-3,000 people were dying, and if we could just work a little harder, or put it a little extra time in, then maybe we could save some people's lives. That's what we really, really thought. And so we're, who's got the latest version of this and where's that and so on. It's like Microsoft Word, right? Where version 1 dash final dash really, really final dash use this one, right? Everybody's had those kinds of file names before. And that's sort of the nature of the stack. Of course, the alternative for Jupyter Notebooks is to just write it in like a VS Code or a PyCharm or something like that. And those tools are really good for developing stable code, right? Because they're built for software engineers, but they suck for data exploration and data analysis because, well, that's not what they were made for. And so despite the kind of popularity and sort of resurgence of building these types of AI projects, there aren't really any good tools for actually doing it. So that's kind of where Zerv comes in. Do you have a time? How much time do I have left? 18 minutes. 18 minutes. All right, perfect. So what we're trying to do here at Zerv is build something that can solve a lot of these problems in terms of the way we develop projects. So how many students do we have in the room? Any students? Okay, fair number of students. And how many professors? No professors. And people that work out in industry. Okay, good. So we're about half and half students. For the students, you guys have all used Jupyter Notebooks. You remember the first time you set up Python on your computer? I've taught a few data science classes, and that's always fun. You get to spend the first week or so trying to get everybody's computers actually working. It's like trying to get your mom to install Jupyter or something in terms of like, getting everything going because of all the issues, right? First you have to install it, and then you've got like dependency problems like, oh, I wrote my code using, NumPy version 0.19, but really this isn't compatible with this other package, so I need to upgrade to some other thing. And then you send your notebook to somebody else and it's a different environment and you're like, what's going on? Like problems, right? So that's the first thing that we tried to tackle here is a common dependency framework. So when you have a project built in Zerv, it's all using the same dependencies. And so think of, I've mentioned Microsoft Word before, think of going from Microsoft Word to Google Docs. Where, if you've ever worked collaboratively in a Google Doc, you can see where other people are editing and working, right? You can see, you got the little circles up top where you've got the people that are participating in your notebook, and if they're typing, you can see them typing, and you can have 8-10 people working in the same project, editing code, so on. That's the paradigm that we're trying to go for here with Zerv. But we're all working from the same place where we've got all the same Python packages installed. We can set up environment variables. We can, build the environment that we want. And then the canvas is supported by that Docker image that's created when you do that dependency management. And then Zerv works in layers. This particular project that I wanted to build here is related to call centers. So imagine that you had a call center that you were trying to manage, and that call center is getting calls constantly from people. In this case, we've got a bank call center, and the bank is getting calls about, hey, what's this transaction? Or, hey, can I check my account balance? Or whatever it might be. In this case, it's simulated data here. So this first layer is strictly simulated data, and because I don't actually have a call center. And so the first thing I needed to do was actually generate some calls. And so I wanted to set up a process for using these large language models to robustly sort of generate a good variety of phone calls that are coming in. And so what I've got here is setting things like the average hold time on particular days. I simulate a time series that shows what's going on there. And then I work with large language models to come up with 3 or 4 different kind of parameters. And so this guy here is how many minutes the person is waiting on hold. This one is generating a topic that the caller might be calling about. And so that's that one. And then this guy here is a description of the caller, things like their social status, wealth, race, that sort of thing. And then all three of those processes. And then this one selects the participants in the call. So in another part here, I've got these agents. I'm using a large language model to kind of describe them. So in this case, the audio creation model that I'm using from OpenAI has 9 different voices. And so I coincidentally have 9 different agents in my call center. And they all have different voices. And I asked the large language models to give them all different strengths and weaknesses. So Alloy here is a methodical problem solver, excels in organizing complex data, very good at managing high volume calls, etc. And so each one of those people, there's 2 people in particular that are very bad at their job. And so this is kind of like one part of the project where I'm sort of generating the, I guess, metadata around what's going on in the particular people that are getting calls. So I'm selecting the caller and the agent here, and all 4 of these merge together into another call. In this case, I'm using O1 from OpenAI, and so I ask it to generate a script of a conversation between the caller and the agent, and I give it some parameters and so on that are being dynamically generated from these other OpenAI calls. Actually, not all OpenAI. So this is Anthropic here. Some of these are using Bedrock. Bedrock is Amazon's or AWS's LLM framework, where you can select all kinds of different models and so on to use. So like Dolly or any of these here. So you can select lots of different large language models to work with. And that's our LLM integration there. And then speech to text or text to speech. So first we generate a script, and then we are going in and asking it to convert it into an actual conversation. And that's, again, using a large language model. And then naming those files and storing them. So you've got a file system out here. And here are all the calls that get generated. And then I want to go ahead and analyze those. So that whole first step was all about, like, okay, I don't actually have any data, so let's simulate some. And so I wanted to do 4 different analyses. Now, before the large language model thing, how would you think about kind of tackling this problem? It's actually pretty challenging. So you'd use some sort of a speech-to-text model. In actuality, that's what I did. I converted those simulated conversations back to text using Whisper. So Whisper is one of the most common, best working speech-to-text models. And then I suppose you could do some kind of a sentiment analysis or maybe some topic modeling or something like that. But the large language models make all of that stuff basically obsolete because they can just read the transcripts and come back with either summaries or analysis or something like that. And that's what I tried to get at here. So I did, starting out, an analysis by day. In this case, I'm reading in from Snowflake. So you'll notice here I'm mix and matching languages. So this is a SQL query. How many of you guys are SQL, bright SQL? Yeah, okay, some SQL people. So this is querying a Snowflake database. And then one of the interesting things about the way the architecture is set up here is that it's language interoperable and it's not in memory. So we've separated compute and storage in terms of the way this analysis goes. So when I run this SQL query, what's coming back is a table, right? Like you might get in a DB2 or whatever you're using to write your SQL, MySQL or whatever. You get a table back. But every block here that runs, it serializes and stores the data that it creates on disk. So I don't have the problem of, oh, my web browser crashed, I've lost all my results. So I can share this. If I shared this canvas with you, you'd be able to log in and see all the results without having to run all the code, which is really different from the experience in Jupyter. So this is all running live online in AWS. So when this block runs, it produces that table, but when it serializes it in a very particular way. So in this case, it might serialize it as, say, a Parquet file. And of course, Python knows how to interact with Parquet, and R knows how to interact with Parquet. And so each block, when it runs, there's a deserialization step where it reads back in the data in the right format. So suddenly for basic data types, I have language interoperability. So if I have R coders on the team, down at the end of this part of the project here, you can see here is a Python block and here's an R block. They're visualizing the same data, but they're using different languages, and they're both connected to a Python block. So you can share data between languages and across teams. So if you had a multi-language team where maybe you've got these kind of crusty old statistics guys and gals that are using R, well, they love R, and R is great for some things. I learned R. That was the first, when I was in grad school, that was the first programming language that I learned, along with SAS. If any SAS coders? All right. So yeah, SAS stopped innovating in like 1987. So anyway, it's good, I guess, that they're dying off. Wait, we're pretty close to SAS headquarters, right? North Carolina? Yeah, anyway, it doesn't matter. So language interoperable here. So it's cool to be able to see a ton of people in the same project doing this stuff. But what you're actually seeing here is I asked the large language models to read all the transcripts for the day and give me the percentage of calls that could have gone better. You know, right? So you could be more specific, more descriptive in your description of what's going on here. But but I've just charted it out here, and so suddenly I've got kind of an analysis. And of course, I have no knowledge of how call centers actually work. So I'm just strictly relying on the large language models here. But the prompt engineering on that stuff could be really sophisticated to be able to produce some really cool stuff. Another thing I did was compliance violations. So I randomly sampled from my calls. In this case, I'm doing 50 different transcriptions. And I want to ask the large language models to evaluate the calls for whether or not they had violations in terms of compliance, right? So in this case, there was one in the random sample that I processed, and it was that the person had given out account information without doing a proper verification of somebody's account, right? So they didn't say, give me this number or whatever and verify the person. One of the things you'll notice is this thing that says fleet launch here, and that we're doing 50 concurrent runs. So in this particular case, what I've done is what we've got is a feature called the fleet. And so if you've ever used ChatGPT, everyone in this room has used ChatGPT, yeah? Yeah, awesome. It's slow, right? Like it takes forever to get an answer, because it's printing out one word at a time. Even if you use the API, it's pretty slow. So it might take 2-3 minutes to come back with a response. So 50 concurrent prompts, or 50 prompts running 2-3 minutes a piece, you're looking at like 2 hours of compute there to actually get that analysis done. But the fleet is a patented process that we came up with where we use serverless technology to submit all of the requests simultaneously. So it's the same cost of compute, but it happens in terms of 50 serverless requests all happening simultaneously instead of having to do them one at a time. And it's only one line of code. It's this spread function that we've created. So sampled list is just a Python list, and we're spreading it across this serverless compute. So all of these processes happen, all of these requests happen at once, and you see this block ran in 14 seconds. And so we got all 15 of those responses back in 14 seconds. And that analysis here results in a data frame that ends up getting printed out to Snowflake with all the potential compliance issues. So that's pretty cool. Then an all call center analysis where I asked it to look at all the calls that we've done and kind of review them and give me the big issues. The number one issue turns out was extended hold times. That's sort of by design. The data set I created to describe the average hold time was like the average was 12 or 13 minutes or something. So it's not, I suppose, surprising that that's the number one thing. But a few other interesting things came up as a result of that analysis. And then lastly, an analysis by agent. So the agent analysis was interesting because you can take an individual and just sort of immediately get a performance evaluation on that person in terms of like how they're doing, how people react to them, how often people get upset on their calls, that sort of thing, and you can get a really interesting review. So one of the things, if we had time, that we could look at is we can compare this performance analysis for each agent, like this is Echoes here, with the description that I gave it at the beginning, saying what their strengths and weaknesses are, to sort of evaluate whether or not the model's got it right and what the potential issues were and so on. So lots of really cool things that you could do there. The last thing I want to show you, about 5 minutes? Nice. Okay, perfect. Is the API builder. So did something really trivial here. But in terms of how many data scientists in the room? Yeah, okay, awesome. And for those that raise their hands, how many of you could build an API from scratch and host it? And spin up all the servers and do the cloud stuff? And yeah, okay, so not nearly as many, a couple. What we did here was build an API builder that's actually really interesting in terms of like giving people the capability to do this stuff where they might not be able to under other circumstances. So with this API builder, you've got a controller here that lets you define the URL and set up security. So if you want to use like an API key or something like that, specify memory and all that kind of thing. And then you can add routes. So in this case, I wanted a get route with an API route with this /compliance. So I just wanted an API that would return any compliance issues for that particular day. So if I wanted to add another route, it would be just as simple as dragging another route on here, and I could go in and say, okay, in this time it's a post request, and maybe it'd be /predict or something like that, and I can go in and say, okay, you're going to get a payload, and that particular payload is going to have a particular structure, and you'll get a particular response, and so on. And then all you have to do is write the code for what the API does, click deploy, and you're good to go. In this case, this one's already deployed. I can download the source if I want to deploy it somewhere else. This would be like the fast API stuff, all the Kubernetes setup files, the Docker container, all that stuff that goes into it. And so it's really straightforward to actually build those kinds of deployments or to do things like create a scheduled job or deploy with SageMaker or something like that. So this is a little bit more than just a development environment. It also gives you all the deployment stuff and the scheduling capabilities and all that sort of thing. But anyway, the point is that it may not be in your particular circumstance that the data science you're doing is saving lives. You might be saving dollars, or you might be making the world a better place in some other way. You're trying to accomplish some goal, but a lot of folks are held back by the toolkit, and there's some interesting stuff coming here. So Zurb.ai is our website. We do have a free tier, so if anybody wants to use it, it's not a sales pitch, but it's an application that's available. It has a community edition and so on. So last thing I'll say is that it's designed also to be self-hosted. So data is often really sensitive, and so if you're using it for data that's sensitive, you might not want that data leaving your VPC. And so the compute and the data storage and stuff all happen in the user's cloud environment rather than having to be sent out to a third party to actually be analyzed and so on. So let me stop there, and I think I have a couple of minutes for questions. I'd love to answer them. Any questions? All right, hit it.
Is there a way to edit scripts along the pipeline and see how the outcome will change within this framework?
Oh yeah, all of this is editable. These are just code editors. So I could change anything I want and rerun everything. I just had it all run here, to save time. Does that make sense? Yeah, it's just a coding environment, really.
I didn't notice that.
Oh yeah. These are just this is a Python code block, and I can just I could change anything I want and rerun it, that sort of thing. Mm-hmm. Okay, well, thanks everybody. Appreciate the attention.